Hello, welcome to this tutorial on the image analysis of some ribosomal data that has been acquired with an electron microscope and that we will process with Scipion. This tutorial was prepared for an EMBO course that was given on September 2017 at Birkbeck College as an EMBO course. Okay, so this tutorial will cover simply the stages from acquiring the micrographs to having a first initial volume that would be further refined. So we will see how to process this in Scipion. We will see that we have several stages that we have colored with different labels. So for instance, those steps related to the micrograph processing have been labeled in red. Then in blue we have the particle picking. Then we have a stage in green in which we do 2D pruning and particle classification. Then we validate our classification step with these blue boxes. Then we will construct our initial model and we will validate our initial model. Okay, so let's start from the beginning. So the first step is to let Scipion know where the micrographs are. So if you want to import some movies, for instance, then you would click on the left menu where you have all the steps that are available. So you would click here and import your movies. So you would have to find where your movies are, which are the pattern, for instance, all the MRCS files. Then you would have to give parameters regarding your acquisition. Particularly important are these the kilovoltage of the microscope, the spherical aberration, the amplitude contrast, and the sampling rate. And also, if you have the dose per frame, normally this is given so that some dose correction can be done. So we already did that, and this workflow here actually represents what has been done. So we will review some already solved project. So what we did here is we found our movies, we gave the pattern. You see, you have all the parameters here that were used for that acquisition. So the output of this step is a set of movies. So we have recorded 37 movies of this size, and each movie contains 18 frames. So if we press on Analyze Results, what we have is the list of movies that we have imported. Okay, so the first step is to check whether the camera gain at that moment was correctly handled. So normally DDDs correct for their own gain. So this gain is calibrated regularly, and what we should see here is simply a residual gain. So if we analyze results here, we see that the residual gains, these patterns are standard, so they are common from different cameras, and this image, this residual gain should be 1. So if the gain has been correctly corrected, then there should not be any gain anywhere. So if we, for instance, look for the histogram of this residual gain, we see that the maximum and minimum values, they are very small, they are pretty centered around 1. So this image, these movies have been correctly compensated for the movie gain. And we can check the parameters for this one. So you have to look for which are the movies that you want to analyze. So for instance, we chose the imported movies. This one didn't exist at the moment we run the protocol. Then this means that we will analyze one frame out of 3, so frames 1, 4, 7, 10, so on. And since there are only 37 movies and we want to analyze just one of them, so we give a movie step of 50. So it means that it will analyze movie 1, 51, 101, but there is no 51, so only one will be analyzed. Okay, so we have checked that the movie gain was correctly compensated. Then the next step is to do a global alignment. So the global alignment is a process that aligns the frames to compensate for the beam-induced movement. So we choose our movies. We have to say for which are the frames we want to align, so from 1 to the end. And you can do some binning here. Also, while aligning, you can you have to estimate which is the shift between one frame and the next. And because of the noise, there can be a spurious local maxima of the correlation. So if you filter the frames, you remove some of these spurious maxima. So we filter at 4 angstroms. This is the default value. We used XMIP correlation alignment that is similar to motion core, but it is more robust to errors in the estimation of the frames, frame shifts. So we compensated for the global alignment, for the global movement, and we can see here some movies, and in each one of these power spectra, what we have is the power spectra before aligning and the power spectrum after alignment. So you can see that tone rings are better seen in this left area than in the right area. So that means that the global alignment did something really useful. We can check here, for instance, what is the shift that has been corrected. So we see that from frame 0 to frame 1 there was some significant shift, or in X the X values are very small, but the Y values, you see they go from 0 to -14. So that means that there was a significant shift in Y. So the global shift correction has compensated all these local shifts or global shifts, and this is kind of the trajectory that the sample had within the electron beam. So you could verify all these movements. For instance, this one, you see you clearly see a drift, and it has been compensated. And here we can see that the movement was huge in that case, so in both directions, X and Y. So the global shift correction is really compensating for incorrectly acquired images. They were incorrect simply because they were moving a lot. Okay, so once we have compensated for the global movement, we can compensate for the local movements. So locally, particles can also move independently from each other. So now, once the global movement has been corrected, we can go for optical flow. So you have it here, optical alignment, and the input for the optical alignment is pretty similar to the one for the global alignment. So we choose now the globally compensated movie, and again you can decide from which are the frames that you want to compensate, and then some parameters for the global for the optical flow. So you can use it in GPU, CPU. You can also average a different number of frames. So for instance, you may align from frame 1 to 18, but then only some from frames 3 to 10. Frames 1 and 2 have been skipped because maybe the beam induced movement in those frames was too large, and then from frame 10 to the end they have also been skipped because the dose rate was, or the dose accumulated dose at those frames was already too large. So this was not the case in this example. We summed all the frames, but you can be very flexible in that stage. And then we can analyze the results, and here what we have is how, again, the same representation: globally aligned image, locally aligned image, and the locally aligned image should have stronger tone rings than the globally aligned image. And we can also see here what is the accumulated local shift. And local shifts can be in any direction, so actually what this is representing is the average absolute value of the frame shift. That is why it looks like a positively growing curve. So on average, from frame 0 to frame 1, every pixel moved like 0.25 pixels. And from frame 1 to frame 2, on average, everyone moved about 0.5 pixels, and so on. So the totally accumulated movement from frame 0 to frame 17 was about 3 pixels in each direction. So you can also verify here if there are some images for which the power spectrum doesn't look so good. For instance, this one, we cannot see tone rings in here, so that may be due to the defocus, due to the imaging conditions, due to the movement. So we can check the movement. The movement here was certainly larger than in the other micrographs that we analyzed. And you may decide here to remove some micrographs or not. So let's say that you want to remove this micrograph. So you select it, disable it, and then generate a new set of micrographs, now with 36 micrographs, where you are confident for the power spectra. You may do it here, or you may do it later, as we did with the after the CTF estimation. So let's not do it now. The next step would be to estimate the CTF. The CTF is how the microscope has blurred the images, and the main parameter there is the defocus that has to be estimated from the micrographs themselves. And we have used, for instance, CTF find for this. So once you have your movies, you can go to micrographs, and here under CTF estimation you would have CTF find. So we have already done that. And here you have which are the movies that or micrographs that you want to analyze. These are the optically corrected images, so we have corrected for the global movements and the local movements. Here you can choose a downsampling factor. This downsampling factor is used only for the CTF estimation, and the goal of this downsampling is to make the tone rings more easily seen, so that the algorithm can find them. So the tone rings will be searched in this blue area. So you can choose the blue area by moving these buttons here. So you can say, okay, so you have to concentrate in this area to look for the tone rings, but then you have to be sure that this blue area is valid for all micrographs. So for this would be valid, for this would be valid, let's see, for this it wouldn't be valid, so we would need something wider here. So let's say this one, and the parameters that we chose before are the right ones for this dataset. The downsampling factor, as you will see, what it changes is the size of the tone ring. So let's look at one for which the tone rings are relatively small. So now if I give a downsampling factor, sorry, don't press enter. So if you choose a downsampling factor by 2, you see that now the tone rings are much bigger. So what we are doing is a zoom in the Fourier space. So this downsampling factor actually can be any real number, so you can make it like 1.5, 1.2, and in this particular data set 1.0 is good enough. So there is no micrograph for which the tone rings are so small, so concentrated in the origin that we cannot see them properly. So we would choose the parameters and then go back to our form and launch it. So we did already that, and the output is this table here. So this table here is showing the power spectrum that was observed in the micrographs, and then the power spectrum that is predicted by this defocus. So what we should see here is that the tone rings overlap with experimental data. So here we have, for instance, this is the first tone ring in the experimental data, this is the first tone ring predicted by this defocus, the second tone ring, third tone ring, and so on. So they pretty overlap, and you can verify that for all micrographs in here. You can also sort by defocus. So for instance, this one doesn't overlap so well, so that means the reason is that we cannot see tone rings in this micrograph. So for instance, this one, we could disable it and generate a new set of micrographs. We will not do it now because we have done it later, but you could do it at this moment if you want. We can also see, for instance, some kind of drift that we have in here, or some ice contamination. We would have to look at it. And also you can go to the end of the list to see, for instance, this one was also not correctly fitted, and these ones were not correctly fitted, and probably because they are not good micrographs. Okay, so at this moment you could select the micrographs you like. There are some parameters here like the defocus, then the resolution estimated by CTF find for. So you can see that this resolution is also a good indicator of bad micrographs. This micrograph is not so good. It can give information only up to 18 angstroms, 9 angstroms here, and 2.5 angstroms in this case. So this resolution is based only on the defocus, but as we will see later, we can estimate also the envelope. So for instance, these ones, you can see that the tone rings doesn't fade as, or in this case is much more visible. So the tone rings in the experimental data have already faded, but we still see tone rings in the predicted power spectra. So this is because CTF find is not estimating the envelope. To estimate the envelope, you can use XMIP. This is what we did here. So XMIP would take the same set of movies or micrographs as CTF find. We can choose the same parameters of downsampling, where to look for the tone rings, and also interestingly, this is one of the nice features of Scipion. We can concatenate and use different protocols. So we can use the output of one protocol as the input of another one. So for instance, the CTF that was the defocus that was estimated by CTF find, we can use it as the initial guess for the XMIP CTF estimation. So let's see the results in here. So these results, what we have is now the envelope is estimated from the data. So we can see, for instance, that the tone rings, the predicted tone rings, also fade with the doesn't show. Also fade with the fading experimental data. So we can see how this fading of the envelope limits the resolution to something like 3.5 angstroms. So we can not expect this micrograph to give information beyond 3.5 angstroms. And this is the frequency at which the envelope drops below 1/100th of the maximum value. So if the maximum value is 1, at 3.5 angstroms, the envelope is already 1/100. So that means we have divided the information by 2 much. Then XMIP also allows us to estimate many other quality criteria. For instance, this one here, called the CTF margin, shows how strong are the tone rings with respect to the noise signal. So we have noise in this spectra. So how strong are the tone rings with respect to this noise? So we can see here we have sorted by the margin. The margin is the larger the better. So these tone rings are barely visible. Here they are barely visible. And if you go to the other extreme, these tone rings are very, very visible with respect to noise. So you may put a threshold on how strong you want your tone rings to be visible. Actually, the algorithm, it already provides some suggestion of which micrographs to remove. So there have not been removed yet, but it already suggests some micrographs to remove. So for instance, you can say, okay, remove these automatically suggested micrographs. So from 37 we go to 33. 4 of them have been automatically rejected. This rejection criteria is rather conservative. There are many more that you would like to remove. For instance, this one, you can see that the envelope is not correctly estimated. The focus itself seems to be, but the envelope is not. And the reason is that it seems to be rather strange, this power spectrum. You cannot see the tone rings actually very well, so you may remove it. So you would disable it, and you can look for other micrographs that are not so good. So for instance, this one has some ice contamination and probably some drift, so you wouldn't like it either. There are some others, like this one also was it was not clear, the estimation of the CTF, so all the tone rings go very much to the high frequency, so that means that probably you may have aliasing in there. Then there are some other micrographs like this one where the background is growing. So you can see that because you have these high values at high frequency, so you wouldn't like that either. And for any one of these micrographs, for instance, let's say this one, you can verify how the CTF was fitted to the data. So you can analyze the CTF itself, you can do a radial average, you can also do an analysis by direction. You can look at the power spectrum. This is the power spectrum at one direction. This is the radial average of that power spectrum. You can check what was the CTF fitted. So it is a pretty good estimated CTF. You can analyze the envelope of that. You can analyze the background of that. Many other things. So at the end, when you are sure of your data set, then you would create a new set of micrographs. I will explain now some other criteria that you may use to decide whether your CTFs are good or not. So this is the criterion of the CTF estimate. So this is an error measure. So if the CTF is well estimated, this value should be very small. So you see here that this one was not small at all, this one was not was the second largest, and very well estimated CTFs, they have values around this one. This unfortunately these values depend on the dataset itself, so there is no absolute threshold that we can give for all datasets, but you can see that it is an error measure, so the smaller the better. Then you can also look at the first zero. So this is the frequency at which the CTF first crosses the zero value. So you may look at the extremes to look for incorrectly fitted micrographs or micrographs for which the CTF was not so good. You can also analyze the defocus ratio. So this is all micrographs are estimated in a 2D way. So there are two different defocus, one in one direction like this one, and one in the perpendicular direction. So you have the estimate of the two defocus in each one of the directions, and you can compute the ratio between the two. So if there is no astigmatism, these two defocus should be exactly the same. If there is some astigmatism, then these two defocus will differ, and this is the ratio between the two. So you can look for the most different defocus and see if still they are okay. You can also look at the other extreme to see if there has been some problems with those. And also you have some other criteria here. For instance, one that is very useful is this correlation between the 1 1/3 tone rings, and also what is the correlation of the experimental power spectrum and that experimental power spectrum rotated 90 degrees. So if there is no astigmatism, this correlation should be very large. So we can sort by this. This is the worst correlating image, and we can actually see that they are not so good. Also, for instance, if you have drift, like in this case, the correlation with itself rotated 90 degrees is very low. If you go to the other extreme, there should be pretty round power spectra. Then you can also look at the correlation. So very badly correlating images between the power spectrum predicted and the observed power spectrum between the first and third zeros. So they are suspicious, and actually all these micrographs are incorrect. And then this, on the other extreme, we would have the best correlating images. So between the first and third zero, the predicted CTF and the observed CTF, they correlate pretty well. So based on all these criteria, you would choose which are the micrographs that you would like to keep, and we have done already that. And these are the micrographs we chose. So from 37 micrographs, we chose only 28. So we threw 9 of them because we didn't like the power spectra or the CTF or how it was estimated. And then you continue to your analysis. There is a point here. If the algorithm fails to estimate the CTF, then you can re-estimate. So let's say that we want to re-estimate this one. So you go to recalculate CTF, and you have to give where to look for this for the tone rings. So you would draw here, which is the area where the tone rings should be looked, and then you have to draw the first zero of the CTF. So now you draw. You can adjust your circle to the observed data, and every time you change your drawing, the defocus is updated in this window here. So we may do it again. So we have estimated about 10,000 angstroms, or 1 micron of defocus for this micrograph. And then once you're happy with that, you would press OK, and you can later launch all these CTF re-estimations in a batch process. We will not do that because we are happy with our CTF estimates. It was only a problem of the micrographs, or mostly of the micrographs. Good. So this would cover the first part of the analysis. So analyzing what is the quality of our data. In the next video tutorial, we will continue with the particle picking, and then we will clean this data, construct an initial model.